Hello, this is Dr. Maria Weber, and today I'm going to work us through a problem that has a set of capacitors inside a circuit, and we have to calculate the equivalent capacitance of this set of capacitors and find the charge and potential difference across each of them. So here's my capacitor setup. I have two capacitors that are in parallel, and those two capacitors in parallel are in series with a third capacitor. What I'm calling capacitor 1 has a capacitance of 2 microfarads, capacitor 2 has 4 microfarads of capacitance, and capacitor 3 has 3 microfarads of capacitance. Now, the first part of the problem, we want to find the equivalent capacitance of this set of capacitors. So what I recommend you do is to break down our capacitors here into kind of sets or components. We see that C1 and C2 are in parallel with each other. So we can find the equivalent capacitance of these two capacitors in parallel, which will then be in series with the third capacitor, and then we can work those through together in order to find the equivalent capacitance. Now I have this board back here before we actually get started on the problem that has a few important pieces of information that we need in order to solve this problem. I don't have room on these boards behind me. So for our capacitors in series, we know that the charge on all capacitors in series will be the same. We know that the potential difference across them sums up. So the total potential difference is equal to the sum across the individual capacitors. And our equivalent capacitance looks like this. 1 over C total equals 1 over C1 plus 1 over C2. And for capacitors in parallel, we have that the charge on the capacitors in parallel sum up together. We have that the potential difference across these capacitors will be the same, and the total capacitance is the sum of the individuals. So maybe jot that down, keep those in mind as we go forward, because I will be referring to them, but I won't have them up here on the board behind me. Okay. So the first thing we're going to do is we're going to find the equivalent capacitance of these two capacitors here in parallel. And I'm going to call that C12. So since C12 are in parallel, we have that C12 is going to be the sum of the individual capacitances. So C12 is going to be C1 plus C2. So that's going to be 2 microfarads plus 4 microfarads. So the equivalent capacitance for these two together is going to be 6 microfarads. Okay? So we could redraw this new capacitor combination like this, where these two that were now in parallel, we've created an equivalent capacitance for them, which I'm calling C12, and that equals 6 microfarads. And then we still have C3 here, which has a capacitance of 3 microfarads. Now, these two capacitors, or equivalent capacitors plus the C3, are in series with each other. And so the equivalent capacitance of these two together is going to be equal to 1 over the equivalent capacitance for these two in series is going to be equal to 1 over the capacitance for this capacitor right here, which I called C12, which was the combination of these two in parallel, plus 1 over the capacitance of C3. Okay? So we've got 1 over the equivalent capacitance is equal to 1 over C12 plus 1 over C3. And so that's going to be equal to 1 over 6 microfarads plus 1 over 3 microfarads. Okay? So if I add these together and take the inverse of them in order to get our equivalent capacitance, we find that the equivalent capacitance for all of these 3 capacitors together is going to be 2 microfarads. Okay? And so we just broke these down into their separate components, identified that these two were in parallel, And these two in parallel were then in series with the third capacitor, and I can use our rules for capacitors in series and parallel in order to find the equivalent capacitance here. So now I've drawn sort of the schematic of these capacitors in our circuit. We took our two parallel capacitors and combined them to get what I'm calling capacitance 1, 2, which is in series with our third capacitor, and then we put those together, combined them in order to get our equivalent capacitance for all three of these capacitors here in our circuit. And so now the next question is we want to find the charge on each capacitor and the potential difference across each capacitor. And in order to do that, you need to know that we've connected this capacitor combination up to a 12-volt battery. Okay, so that's going to be the potential difference across our entire combination of capacitors here. So let's first think about finding the charge on each of our individual capacitors. But before we get any further than that, let's find the charge on our equivalent capacitor. So here I have that the charge of a capacitor is equal to its capacitance times the potential difference across it. So for our equivalent capacitor here, our charge on our equivalent capacitor is going to be equal to the equivalent capacitance times the potential difference across it. So that's going to be 2 microfarads, so 2 times 10 to the minus 6 farads times our potential difference, which is 12 volts. And so then our equivalent charge over here is going to be 2.4 times 10 to the minus 5 coulombs, which is also 24 microcoulombs. Okay, so Q equivalent is 24 microcoulombs. All right. So we have that in mind. Now, in series capacitors, the charge on each of the capacitors is the same. So that means that the Q, the charge on our capacitors here in series, C1, 2, and C3 must be the same, and they're the same as the charge on our equivalent capacitor. So the charge on capacitor C3 is going to be also 24 microcoulombs. So that also means that our equivalent capacitor C12 has a charge of 24 microcoulombs on it as well. But we need to find the charge on the individual capacitors C1 and C2. These capacitors are in parallel, and when we have capacitors in parallel, their charges add together. So we have the charge on our equivalent capacitor, Q12, has to equal the charge on capacitor 1 plus the charge on capacitor 2. So we think about what goes into calculating this charge. We know the capacitance for each of our capacitors, but we don't know the potential difference across them. So before we can get the charge on C1 and C2, we need to think about the potential differences across them. Now, in series, the potential differences across our capacitors add. So we look over here at this equivalent series circuit of our capacitors. We have that the total potential difference has to equal the potential difference across our equivalent capacitor C12 plus the potential difference across our capacitor C3. I'm summing them up together because in series, our capacitors, the voltage across them must add. Okay. So if I look at this, the total voltage, that's our 12 volts coming from our battery. V3, well, we can go ahead and calculate that because we already know the capacitance of C3 and we know the charge on C3. And so then, using this equation right here, we know that the voltage across V3 has to equal the charge across that capacitor divided by its capacitance. Okay, so the potential difference for our third capacitor here is going to be our 24 microcoulombs divided by our 3 microfarad capacitance, and that gives us 8 volts. Okay, so V3, or potential difference across capacitor 3, is 8 volts. And so I'll also write that here. V3 is equal to 8 volts. So I can erase this so I have more room. Okay, now if I want to solve this equation for the voltage across our equivalent capacitor, C12, I get that V12 equals V total minus V3. So that's 12 volts minus 8 volts. And so the potential difference across our equivalent capacitor, C12, is 4 volts. Okay, now why is that useful to us? Because this equivalent capacitor is made up of these two capacitors here, which are in parallel with each other. And when capacitors are in parallel, they have the same potential difference across them. So if our equivalent capacitor, C12, has a potential difference of 4 volts, that means that C1 has a potential difference of 4 volts, and so does C2 has a potential difference of 4 volts. Okay. Now I can use this information, I've got the capacitance, I've got the voltage, in order to find the charge on each of my capacitors here in parallel. Okay, and so I can just use that Q1 is equal to C1 V1, Q2 is equal to C2 V2, okay, and so C1 is 2 times 10 to the minus 6 farads times V1, which was 4 volts, okay, and then that's going to equal 8 times 10 to the minus 6 coulombs, which is 8 microcoulombs, 8 microcoulombs, and then for the charge on our second capacitor, we have that its capacitance is 4 times 10 to the minus 6 farads times 4 volts, and that is going to equal to 1.6 times 10 to the minus 5 coulombs, which is also 16 microcoulombs. Okay? 16 microcoulombs, 8 microcoulombs, and so then we finally found the potential difference across each of our capacitors and the charge across each of our capacitors too. So for capacitor 1, we have the potential difference across it is 4 volts. Its charge stored is 8 microcoulombs. Capacitor 2, its potential difference across it is 4 volts. Its charge stored is 16 microcoulombs. And capacitor 3, its potential difference is 8 volts. Its charge stored was 24 microcoulombs. Okay, so I know that maybe this is a little chaotic. I'm using a bunch of different dry erase boards. I've got a much smaller board than I'm used to in class. And I'm also doing this outside. But I hope that, especially if you watch it a couple of times through, that it gives you a better idea of how you can tackle this type of problem.